Good morning, everyone, and great presentation. I'll start to kind of get the sense of what's going on in Australia. And I'm going to talk about a little bit about the cloud side of things and how we view, say, the emergence of digital twins and beyond. And what I mean by that is how you move from, say, physics-based type models, which predominantly used in the power and utility sector, and how we move beyond to, say, big data type science-based models or data models, as such as machine learning or reinforced learning, AI type things. So I just want to start out with a little bit about how Microsoft and certainly the cloud and most cloud providers is one of the largest power and utilities electricity users in the world, and how we see the changing power landscape emerging. And these are looking at market forces that are also combined with operational challenges. And just have a brief introduction on how these changing landscape is affecting, and I think Alistair mentioned this, renewable energy going up, distributed energy resources also increasing, is putting pressure on IoT and digital transformation. So data is becoming more valuable to be able to use these data to be able to predict and do computations of, say, what is the state of your system in as near as real time as possible. And of course, I think as Alistair mentioned too, you're talking about removing inertia off the grid. It's creating more volatility in the energy supply and demand, matching those. And then these new scenarios of solar and electricity type, solar behind the meter and electric vehicles being able to participate. And this is creating a lot of prediction complexity. And of course, then you have the decrease of thermal generation, which we kind of call the duck curve. Is at that bottom of the duck curve is where you're starting to reach some thresholds of instability in in your inertia from increasing the penetration of renewables. And so fundamental challenges that we see, of course, is the bidirectional flow of electric power, and of course, how energy storage is going to play. But digitization and computation needs have an increasing value because the system is being driven by more stochastic and temporal behavior. So we look at, when you think about using data and digitization, all this data pipes coming in, and you think about how the energy system is starting to merge together. If you think about how traditionally you had just separate sectors of power generation, you had thermal generation, you had combustion of hydrocarbons in transportation, and now we're adding in a ecosystem of that is connecting all these kind of energy sources together, where you have both on generation side and distribution side, you're able to actually generate electricity or consume it. And so this kind of process of digital twins, and at least in my mind, have arise from where you describe a kind of a system, say a generator system, and how you can actually create the digital twin of that from computation. And how this is, merging this into you being able to use that kind of data that's coming off this system and starting to use things like AI and getting data from edge and feeding in data pipes from IoT, and then generating this up, moving this into the cloud, where you have this kind of globally available, unlimited computational resource. And with that kind of global computational resource coming available, it ends up being that you end up starting to think about the system as a whole digital energy twin. And I think that kind of gets at a little bit at what Alistair described in AMO, is what they're looking at the entire system, and rather than just piece by piece. And a big part of that, I think, Alistair also mentioned this need of data, of common data models or standardized data. And we also see that as a big piece of trying to achieve these kind of goals of using, say, cloud computation with a lot of data coming in, a lot of different sources, and a lot of different sources and different types of configurations of data. And so how do you create those common data models that can create a common languages between services, say cloud services, to interoperate with each other and with the data at the same time? And so that's, I think, an approach where common data models, this is for the industry, is a place where there's a lot of good work that can go on. I think Alistair mentioned the IEEE standards, and we view that as a adoption of those as a big piece of achieving cloud capability into the industry. When we think about power and utilities, we see this as digitization across opportunities across all of the kind of operations. And then realizing that there is some of data that is regulated. So it's certainly things like in the US with the bulk energy systems data, BES or BCSI. These are kind of things that are coming off generation or operations side. And we see kind of a trend for, here in the US, there's right now there's a FERC had ordered NERC to look at what it would take to actually put BES type operational data into the cloud. And that's actually a work in progress that is due out this January, report from NERC. And then, on transmission side, there's a mixture of data, but being able to actually get real-time performance and real-time supply and demand controls coming from transmission to give you better operational supply and demand matching. And of course, I think where a lot of work is being done is on the distribution side, and that's kind of the changes, this idea of putting on distributed energy resources, being able to feed back into the kind of market side and how that works, and how that needs to look at also matching the real-time supply and demand equation from transmission. And so there's, of course, and then on the consumption side, this is where the markets are starting to play. What are the new kind of customer models or the new models for unlocking these kind of distributed energy resources? And you really do see a lot of movement in the in this buckets 3 and 4 that is really driving kind of the behind the meter side adoption. And this is where we kind of see the where flexibility in the future, flexibility will come from the distributed side, this kind of prosumer side, as you're decreasing the amount of thermal generation. So there's a broad opportunities across digitization in this sector. And as Alistair mentioned about the Australian Energy Simulation Center, I won't repeat. We've been working with OPAL-RT on this, and we're thinking, I have a small kind of architecture diagram of what cloud actually looks like for those of you not familiar with it. But if you think about cloud, it's kind of a platform that you're enabling here in this bucket in the right-hand top here. You're enabling software as a service. So software providers can put their software on the cloud, and then they're able to kind of leverage all of the tools or data pipes coming in from, say, even from weather, grid data, physical equipment, devices, and sensors. You can bring those in through an IoT hub pipe, and it opens the door for those kind of software providers to use all of these kind of analytics and artificial tools to actually streamline the process and give you insights and that are typically could maybe not be found by, say, a physics-based model. in the sense that certainly when you're talking about maybe models that have a non-linear nature, that it takes some time to converge. So we see that this kind of architecture is what we're looking at and adopting with OPAL on this project. And I mentioned the kind of a little bit about this kind of the power of let me go back a slide. You know, the computational advantage of cloud is on this in the sense that there's a this being able to bring both high AI and machine learning into with HPC to do things a lot faster. And so that allows you to have this kind of scale to be able to use these this kind of platform to be able to enable big data type science algorithms like AI and machine learning. And I'll just follow up with a couple of what I mean from beyond. So here is one of, this is some of the work that we're doing in Microsoft Research to look at how to go beyond, say, the digital twin into looking at neural operators for power systems and transient dynamics. And so as we talked and mentioned that you're moving the inertia from the grid, you're going to a high inertia to a low inertia grid inverter based system. And so that can create, you know, a lot of issues in matching supply and demand and frequency, which is related to phase angle. And so here we're looking at how we can use these neural operators to get inertia constants and feeding in some of the data coming off the system to be able to do those calculations in as real time as possible. And another thing that we're working on from what I would say from digital model and beyond is the state estimation and network effects. And so how we're looking at taking data, sensor data, PMU, SCADA data, grid topology, weather data, and combining that all in together, fusing that together into a machine learning model that can actually cycle and be able to learn from itself and eventually go from, say, prediction to optimization. So with that, I'll just wrap up there and hope we just give you a kind of a broad overview of kind of what we're viewing and how we view power and utilities and the kind of emergence of data and being able to orchestrate software to accomplish some of the use cases of reliability and resiliency in the grid.